All right, with that, we'll go on to our next presentation. I'd like to invite Helen Zhang to deliver the next talk. And Helen, you can go ahead and share your screen whenever you're ready.
Can you see my presentation right now?
Yes, we can, Helen.
Cool. Okay, thanks, Killa. I'm Helen Zhang from the, let's just move this around. Hydrologist from the Environmental Monitoring and Reporting Branch, MECP. Glad to have this opportunity today to give everyone a general idea of what types of groundwater projects the province has facilitated and funded in recent years under the Canada-Ontario Agreement on Great Lakes Water Quality and Ecosystem Health called COA. So first, an overview of what is COA and what how's groundwater represented in it for those who are not familiar with it. COA contained Canada and Ontario's commitment to restore, protect, and conserve the Great Lakes, and its most recent renewal was signed in June 2021. Under Annex 9 Groundwater Quality, the COA 2021 continues to focus on understanding of groundwater influences on Great Lakes water quality and ecosystem health, and on identifying priority areas for action. And the 2021 COA underscores the pivotal role of high-quality groundwater and the importance of understanding of groundwater surface water interactions through continuous monitoring and advanced modeling techniques. And in addition to groundwater, In addition to Groundwater Annex, the significance of groundwater is acknowledged across various other annexes, including nutrients, climate change impacts, wastewater and stormwater, and harmful pollutants. So over the past 3 to 4 years, the Groundwater Annex, along with other annexes mentioned earlier, has supported a variety of projects focusing on groundwater. These projects listed here have covered a broad spectrum of topics, ranging from improving field monitoring and numerical modeling of groundwater surface water interactions, to investigating the pathways through which road salt and nutrients infiltrate and migrate within the groundwater system, identifying sources of contaminations such as PFAS and other contaminants originated from landfills and septic systems. The map highlights tertiary watersheds on the Canadian side of Great Lakes Basin, which is the focused area of COA. The map indicates project locations. Small red dots represent studies on the subwatershed or the watershed scale, and large pink ones for studies covering a basin or broader area. In the following slides, I'll give you a very brief summary of these projects. Basically, just the purposes and main findings, 1 to 2 pages per project. For the interest of time, I won't be able to introduce all of them. I excluded these projects marked in blue from my presentation with the understanding that they were being presented by the project teams on Tuesday's session. Now I realize it may not be entirely true, but too bad I can't add them back in. The next few slides summarize studies focus on the role of good quality groundwater and characterizing and modeling groundwater surface water interactions. This project is a proof of concept effort aimed to predict groundwater levels like weather forecasts. The modeling tool called HDS, you're familiar with that, feeds weather data to a fully integrated groundwater surface water model to simulate hydrologic system dynamics. We select 2 pilot watersheds for this exercise. One is bedrock dominated and drought prone. The other one is sandy with intensive water taking activities. The models have forecasted groundwater depth, recharge, discharge, stream levels, as well as soil moistures up to the next 32 days. Some forecasting products are shown on the right-hand side. The top map shows groundwater discharge volumes along creeks. Bottom map presents depth to groundwater. Click anywhere on the map will give you a forecasted hydrograph of the selected parameters. In this project, we used a fully integrated climate hydrologic models to simulate groundwater discharge dynamics in southern Ontario. The model domains were established at catchment, watershed, and regional scales to evaluate model scaling effects. 11 catchment areas were selected to leverage data collected from the ministry's multi-watershed nutrient study. And the watershed scale model included 7 watersheds housing these sub-watersheds. The regional scale model covered the entire southern Ontario. A big thank you to JSC, who led the project of building the Southern Ontario model back in 2019. This was the foundation of COA projects simulating groundwater surface water interaction across Southern Ontario, to just mention the least. This project simulated a 30-month period from 2018 to 2020. Graphs on the right illustrates model outputs for a couple of sub-watersheds with diverse hydrogeological conditions. And you can see the green line represents stream outflow. Red line is groundwater discharge to the stream. And the blue line indicates base flow index. In the Big Creek sub-watershed on the bottom right, minimum groundwater contributions noted, with stream flow peak in springs and almost no flow during summers. Conversely, the Venison Creek sub-watershed shows a stable stream flow and consistent a substantial groundwater contribution, which is also indicated by the base flow line that has been consistently above the 50% level. This project focused on the Western River sub-watershed, located just north of Sudbury, examining groundwater surface water interaction by quantifying various water sources in the stream flow. Field monitoring was completed between June and November 2021. Monitoring and sampling locations marked on the land cover and quaternary geology map shows the surface water monitoring sites from the headwaters to the watershed outlet, and groundwater sites at provincial monitoring wells and some municipal monitoring wells. The team conducted bi-weekly survey of stream, other surface waters, precipitation, and groundwater. Samples were collected for analysis of stable isotopes and major ions. Using 2 and 3 component mixing models, the project team identified and quantified different water sources in the stream, being surface waters, natural groundwater, and urban groundwater intercepted by the drainage system. This diagram illustrates the estimated percentage of different water sources in the total stream flow along the Western River. Gray arrows represent natural groundwater. Green indicates surface waters, including wetlands and inland lakes. And pink represents urban groundwater, with lighter shades for the summer period and darker shades for fall. You can see in summer, natural and urban groundwater dominated the flow. In fall, contributing from natural and urban groundwater decreased, and surface water contributing almost 80% of the total flow. This project was just initiated in last spring at Alder Creek in Grand River watershed. The goal is to optimize field monitoring and data analytical methods used to characterize groundwater surface water interaction. Hopefully, the insights gained from this project will benefit similar studies in other watersheds across southern Ontario and elsewhere. So far, the team completed a temperature survey along Alder Creek, identifying groundwater discharge sites using stream bed sensors and an infrared camera. Based on that, 2 groundwater monitoring sites were established, each equipped with 4 stations of wells and mini piezometers with temperature sensors and level loggers. Other monitoring sites include 5 surface water stations monitoring stream levels and flows, along with 1 meteorological station. Streambed point velocity probes were also employed in collaborating with the University of Kansas. The rest of the slides introduce studies focused on nutrient and contaminant migration from groundwater to surface waters and on identifying priority areas for monitoring and action. The Park Hill Creek subwatershed is mostly agricultural with low permeable soils and extensive tile drainage, quite typical in the Lake Erie Basin. The main objective was to quantify the spatial and temporal evolution of phosphorus and nitrate, especially within the hyparc zone. From July 2020 to September 2021, extensive field data have been collected from the creek and a transect from groundwater downgradient of the agriculture field to the end of the tile drains and to the creek bed. Several groundwater surface water modeling techniques have been used to assess the impact of land use on water balance and quality. The study affirmed that nutrient transport in this type of watershed setting is controlled by climate events and agricultural practices. Result highlighted that subtle events mobilize nutrients, and tile drainage emerged as the primary contributor to nutrient in the stream, while groundwater contribution was insignificant due to low permeable clay deposits and the losing stream condition here. This desktop study estimated groundwater contribution and its chloride loadings to Northern Lake Ontario. Hydrograph separation at 95 gauging stations was used to estimate groundwater discharge volume. On this map, groundwater percentage in stream flow is highlighted in blue, brown, and runoff percentage in blue. The exercise found that groundwater contribution to Northern Lake Ontario is greater than the overland runoff. Next, they run 12 numerical models and verified this estimation. The modeling results also indicated that the direct groundwater discharge into Lake Ontario along the shoreline is a small portion of the total groundwater contribution. This graph shows the distribution of maximum chloride concentrations collected from over 2,000 sampling locations as the last step of loading calculation. The study found that groundwater transports 12 to 64 kilotons of chloride per year into Northern Lake Ontario. Assuming majority of the chloride is from road salt, and the road salt application rate is much higher, it supports the hypothesis that groundwater chloride concentration has not reached a steady state and will continue to increase. This project assessed industrial sites across Ontario for their potential as PFAS contamination point sources, spanning 6 industrial sectors. Each site was evaluated using an industry-specific decision-making framework to classify it into 3 categories, being PFAS contamination likely, possible, or not likely. This graph illustrates the evaluation outcomes across industry sectors. Notably, no sites were deemed unlikely as PFAS contamination sources, represented as zeros at the top. And the wastewater and petroleum sectors obtained 100% likelihood classification, while fabrication and auto sectors surpassed 80% likelihood. This map illustrates sites classified as likely or possible PFAS contaminations, particularly those located within 1 kilometer of a drinking water well. This project focused on evaluating closed municipal landfills as potential sources of contaminants of emerging concern, CECs, to Great Lakes waters. Ontario has over 4,000 closed landfills, exemplified by this air photo. You can see these sites have often been repurposed and look inconspicuous. and can be adjacent to streams and rural wells. The study investigated 20 closed municipal landfills, assessing the prevalence of CECs in leachate-impacted groundwater. Samples were collected from landfill leachate and groundwater from wells, sieves, and discharges to surface waters near the landfill. The graph illustrates concentrations of various PFAS parameters at each landfill, arranged by ages along the x-axis. Notably, older landfills, close between the 1920s and 50s, exhibit distinctive PFAS characters compared to those closed in the early 90s. The study found that closed municipal landfills can serve as long-term sources of contamination impacting nearby wells and surface waters. And beyond PFAS, is evident that other contaminants of emerging concern could also be present in groundwater near closed landfills. Okay, that's all I had to say today. So do I have time to take any questions?
Yeah, absolutely. And we did get one in, David. So there was a question about, is there any data that any data available on what impact gravel mining washing systems might have on the quantity and quality of groundwater in South Central Ontario? Sounds like many well users are reporting issues with quality and quantity.
Are you sure this is a question for me?
Oh, maybe this was a question for one of the earlier presentations, but sorry, Helen.
That's okay, because I don't know the answer for that.
That's okay. Maybe if this might have been for Hazen earlier. Hazen, did you want to maybe come up and speak to that question a little more?
Sure, but I think it's really a question for MECP or the OGS. Water quality is a provincial responsibility, and this is a question of local impact, so I can't really comment on it. Or the alternative is Environment Canada, so ECCC, which does anthropogenically influenced water chemistry studies.
Yeah, I can say so my kind of topic today is the focus on COA, and this is not a topic COA projects has researched on, but I'm pretty sure the quarry operations, they do have their ECAs, and they do have their monitoring programs, and there are database existed somewhere, and I would assume this is maybe OGS based on their operating license. They need to submit, but I definitely don't have those information on hand.
Okay, thanks. Thank you both, Helen and Hazen, for covering that. Hopefully that helps answer your question there, David, somewhat. Maybe we'll be able to get back to you with some other resources. And with that, I guess we're coming up to time.